This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is the maximum power transfer theorem as applied to DC circuits. Our objective is to learn at which conditions a circuit delivers maximum power to a variable load resistor. Additionally, we'll discuss efficiency at and at other than maximum power conditions. This lecture operates under the presumption you are marginally skilled in Thevenin's theorem, to a lesser degree Norton's theorem and source conversion. If you're not familiar with these theorems and techniques, please take the time to check out these lectures, available at the Big Bad Tech channel. Additionally, this lecture makes use of spreadsheet and graphing software, particularly Microsoft Excel. This, or an equivalent software resource, makes an incredibly handy instructional resource when visualizing circuit properties at or near maximum power conditions. Bottom line up front, a variable load resistor will experience maximum power from a circuit when its resistance is equal to that of the Thevenin's equivalent resistance for that circuit. This is to suggest maximum power is delivered to the load when R load equals RTH. As we'll soon learn, this isn't exactly the most efficient of conditions, but does however represent peak power delivery conditions to the variable load resistor. Consider this series parallel circuit supplying variable load resistor R load. R load will receive maximum power when R load is exactly equal to the Thevenin's equivalent resistance for this circuit. By all means, pause the lecture and see if you can use Thevenin's theorem to find the Thevenin's equivalent voltage ETH and the Thevenin's equivalent resistance RTH. If you're tracking, you should have obtained the following results. If you've been following this lecture series in its intended order, you'll realize that this is the exact same circuit we used to introduce Thevenin's theorem. Here's a review of the steps we used to determine the Thevenin's equivalent of the circuit. We need to solve for two properties, the Thevenin's equivalent voltage and the Thevenin's equivalent resistance seen by the variable load resistor. To solve for the Thevenin's equivalent voltage, we need to remove the load resistor of interest and determine the open circuit voltage. The load resistor removed from consideration, the open circuit voltage at terminals A and B would be the voltage across resistor R2. The application of the voltage divider rule demonstrates that Thevenin's equivalent voltage seen by the variable load resistor would be 18.2 volts. To solve for the Thevenin's equivalent resistance, we need to remove the load resistor and the source, and then determine the resistance at the terminals of interest. With the load resistor removed from consideration and the voltage source replaced with a short circuit, an ohmmeter placed at the terminals A and B would see R1 in parallel with R2 for a Thevenin's equivalent resistance of 267.1 ohms. The Thevenin's equivalent circuit seen by the variable load resistor would therefore be an 18.2 voltage source in series with a 267.1 ohm resistor in series with a variable load resistor R load. Let's use this Thevenin's equivalent circuit to demonstrate an application of the maximum power transfer theorem. The maximum power transfer theorem states the load resistor will experience maximum power from a circuit when its resistance is exactly equal to the Thevenin's equivalent resistance for that circuit. Let's see if this is the case. When R load is set to 267.1 ohms, note that Thevenin's equivalent voltage source ETH sees a total resistance of exactly twice the Thevenin's equivalent resistance. An application of the voltage divider rule demonstrates the load resistor will drop half the supplied voltage, in this case 9.1 volts. An application of Ohm's law demonstrates current through the variable load resistor, R load at maximum power conditions will be 34.1 milliamperes. An application of the power equation demonstrates the variable load resistor will dissipate 310.5 milliwatts of power at maximum power conditions. If R load was set to any other value, lesser or greater, it will dissipate less than this amount of power. Let's prove this to ourselves by dialing R load down to 133.6 ohms, or half the Thevenin's equivalent resistance, and perform the same analysis. As an exercise to the viewer, I invite you to determine the voltage across the load resistor, the current through the load resistor, and the power dissipated by the load resistor when the load resistor is set to 133.6 ohms. By all means, pause the lecture and try this yourself. If you're tracking, you should have obtained the following values. When R load is set to 133.6 ohms, an application of the voltage divider rule demonstrates the load resistor will experience a reduced 6.1 volt drop. Application of Ohm's law demonstrates current through the variable load resistor, R load at less than maximum power conditions to be 45.4 milliamperes. An application of the power equation demonstrates the variable load resistor will dissipate 276 milliwatts of power at less than maximum power conditions. In these reduced resistance conditions, R load, being a smaller resistance than maximum power, draws more current, however, drops less voltage, and therefore dissipates less power. Let's switch tactics and crank our load up to 534.3 ohms, or twice the Thevenin's equivalent resistance. As an exercise to the viewer, I invite you to determine the voltage across the load resistor, the current through the load resistor, and the power dissipated by the load resistor when the load resistor is set to 534.3 ohms. By all means, pause the lecture and try this yourself. If you're tracking, you should have obtained the following values. An application of the voltage divider rule demonstrates the load resistor will experience an increased 12.1 volt drop. An application of Ohm's law demonstrates current through the variable load resistor, R load, at less than maximum power conditions to be 22.7 milliamperes. Finally, an application of the power equation demonstrates the variable load resistor dissipates 276 milliwatts of power at less than maximum power conditions. At these conditions, our load, being a larger resistance, drops more voltage, however, draws less current, and therefore dissipates less power. You note when our load is less than RTH, it experiences less voltage, more current, and less power. Similarly, when our load is greater than RTH, it experiences greater voltage, less current, and less power. That's the point. At maximum power conditions, our load is a point when two interrelated values, voltage and current, form a maximum power product.